A haloalkane molecule is formed when a hydrogen atom in an alkane molecule is replaced by a halogen atom. Some typical haloalkanes are illustrated here. This class of compounds is also called alkyl halides. Haloarenes are formed when a hydrogen atom in an aromatic compound, such as benzene, is replaced by a halogen atom. These compounds are also called aryl halides. Many organic compounds that contain halogens occur naturally. Both synthetic and naturally occurring halogenated organic compounds have important uses in medicine and research. Chloramphenicol is a naturally occurring substance produced by soil microorganisms. As you can see in the structural formula, it contains 2 chlorine atoms. Chloramphenicol is used as an effective drug in the treatment for typhoid fever. The thyroid gland, a butterfly-shaped gland at the base of your neck, produces the hormone thyroxine. Notice the 4 iodine atoms in the chemical formula. A lack of dietary iodine can lead to a deficiency of this hormone, which can eventually lead to goiter. Many countries have mandated that small amounts of iodine be added to table salt to minimize the risk of goiter. Chloroquine, a synthetic compound, is used for the treatment of malaria. Halothane is used as a general anesthetic during surgery. These compounds are used in industries as solvents for relatively non-polar compounds, and also as starting material for the synthesis of a variety of organic compounds. Haloalkanes and haloarenes can be classified in several ways. One way is to classify them based on the number of halogen atoms. Chloroethane, a monohaloalkane, and chlorobenzene, a monohaloarene, each containing 1 halogen atom, are shown here. Dihaloalkanes and dihaloarenes have 2 halogen atoms in their formulae. Trihaloalkanes and trihaloarenes with 3 halogen atoms are also known to exist. Based on the hybridization of the carbon atom to which the halogen atom is bonded, monohalo compounds are classified as alkyl halides, allylic halides, benzylic halides, vinylic halides, and aryl halides. In alkyl, allyl, and benzyl halides, the halogen atom is attached to an sp3 hybridized carbon atom. On the other hand, in vinyl and aryl halides, the halogen atom is attached to an sp2 hybridized carbon atom. We'll start with the alkyl halides, or haloalkanes, which have the general formula Rx. R here represents an alkyl group. In these compounds, the halogen atom is bonded to an sp3 hybridized carbon atom. The homologous series of alkyl halides can be represented by the formula CnH2n plus 1x. based on the nature of the carbon atom to which the halogen atom is attached. The alkyl halides are further classified into primary, secondary, and tertiary. In primary alkyl halides, the halogen atom is attached to a primary carbon atom. For example, ethyl chloride is a primary alkyl halide. In secondary alkyl halides, the halogen atom is attached to a secondary carbon atom. Isopropyl chloride shown here is a secondary alkyl halide. In tertiary alkyl halides, the halogen atom is attached to a tertiary carbon atom. For example, in tertiary butyl chloride, the chlorine atom is attached to a tertiary carbon atom. You need to be able to recognize allylic carbons. Allylic carbons are carbon atoms bonded to a carbon atom that is doubly bonded to another carbon atom. As the illustrations here show, allylic carbons are one position away from a double bond. Allylic carbons are sp3 hybridized. Allylic haloalkanes have halogen atoms attached to allylic carbons. In benzylic halides, the halogen atom is bonded to a carbon atom with sp3 hybridization, that is linked to an aromatic ring. In primary benzylic halides, the carbon attached to the halogen has only one carbon-carbon bond. Here are secondary and tertiary benzylic halides. In a secondary benzylic halide, the carbon attached to the halogen atom is bonded to two other carbons. In a tertiary benzylic halide, the attaching carbon is bonded to three other carbon atoms. It will be helpful in your chemistry studies if you can identify vinylic carbons or alkenyl carbons, as they are sometimes called. Vinylic carbons are sp2 hybridized and are double bonded to one carbon atom. The vinylic carbons in two different molecules are shown in the illustrations here. Vinylic halides have a halogen atom bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond. Two examples of vinylic halides are shown here. In aryl halides, the halogen atom is bonded to an sp2 hybridized carbon atom of an aromatic ring, as illustrated here. Learning the proper nomenclature of organic molecules is very important, and it takes a lot of practice. Many compounds have common names as well as systematic IUPAC names. The common names of alkyl chlorides can be found by giving the name of the alkyl group followed by the halide. In the IUPAC nomenclature system, they are named as halo-substituted hydrocarbons. Let's write the IUPAC name of the given molecule. The longest continuous carbon chain has 4 carbon atoms, and hence the root word is but. Since the longest carbon chain is saturated, the primary suffix is -ane. Thus, the name of the parent carbon chain is butane. We then need to identify the substituent and its location. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the substituent is attached. We see that the carbon atom with the substituent chlorine is in position 1. Thus, the name of the given compound is 1-chlorobutane. Now try these practice problems on your own. Give the IUPAC names for these two molecules. Are they primary, secondary, or tertiary haloalkanes? The IUPAC name for the molecule on the left is 2-chloro-2-methylbutane. It is a tertiary haloalkane as the chlorine is bonded to a carbon linked to 3 other carbon atoms. The IUPAC name for the molecule on the right is 3-chlorohexane. It is a secondary haloalkane. Notice that the chlorine is bonded to a carbon linked to 2 other carbon atoms. Apply your skills in a new way. Draw the formulae for the compounds here. Try these on your own before checking the answers. The illustration on the left gives the trans isomer of 2,3-dibromobute-2-ene. Can you draw the cis isomer? Shown here is the cis isomer of 2,3-dibromobute-2-ene. The common names of haloarenes give the name of the aryl group followed by the halide. Common names may use the prefixes ortho, meta, and para to indicate relative spacing, 2, 3, or 4 carbons between the halogen atoms. In IUPAC nomenclature, haloarenes are named as substituted arenes, listing the location and type of the halogen atoms. Let's work through some practice problems together. What are the IUPAC names of these compounds? All 3 molecules are benzene derivatives. Remember that if more than one similar substituents are present, then we must give the location of each and include prefixes indicating the number present. The common and IUPAC name for molecule A is fluorobenzene. Molecule B is often called meta-dichlorobenzene. Its IUPAC name is 1,3-dichlorobenzene. The common name for molecule C is symmetrical trichlorobenzene, while its IUPAC name is 1,3,5-trichlorobenzene. Dihalogenated compounds with the same type of halogen atoms can be classified based on whether the halogen atoms are on the same or adjacent carbons. If the 2 halogen atoms are bonded to the same carbon atom, then it is called a geminal dihalide. Geminal dihalides in the common system are named alkylidene halides. In the IUPAC system, they are named 1,1-dihaloalkanes. Thus, the molecule shown here can be called ethylidene chloride. Its IUPAC name is 1,1-dichloroethane. If two halogen atoms of the same type are bonded to adjacent carbon atoms, it is called a vicinal dihalide. Vicinal dihalides in the common system are sometimes named alkaline dihalides. In the IUPAC system, they are named 1,2-dihaloalkanes. For the molecule shown here, the common name is ethylene dibromide. Its IUPAC name is 1,2-dibromoethane. Here are some additional practice problems. Try to name molecules A, B, and C on your own before proceeding. Molecule A is 1,1-dichlorocyclopentane. Molecule B is correctly named 2,4-dibromopentane. In this molecule, you will get the same name whether you start counting from the left or the right. Molecule C is 7-bromohept-1-ene. You might see this written as 7-bromo-1-heptene, using earlier IUPAC guidelines. The double bond takes priority over the halogen atom, so carbon number 1 is at the far right. Practice is the key to learning organic nomenclature. Here are 2 problems to try on your own. What are the common and IUPAC names of these compounds? Vinyl bromide and allyl chloride are the common names of these molecules. What are their IUPAC names? The common name of compound A is secondary butyl bromide, and its IUPAC name is 2-bromobutane. The common name of compound B is neopentyl bromide, and its IUPAC name is 1-bromo-2,2-dimethyl-propane. The common name of compound C is tertiary butyl bromide, and its IUPAC name is 2-bromo-2-methyl-propane. The IUPAC name for vinyl bromide is bromoethene. No number is necessary for the position of the bromine atom. Whichever carbon atom it is attached to must be the first carbon. The IUPAC name for allyl chloride is 3-chloropropene. Because of the double bond, the leftmost carbon is at position number 1. Let's practice another important skill. That is, drawing structural formulae from names. It is best if you start with the end of the name, with the carbon backbone, and work forwards. Try them independently before checking the answers. The correct structural formulae are shown here for 2-bromo-2-iodobutane and 1-fluoro-2-methyl-cyclohexane. Remember that if there is more than one substituent, they are listed alphabetically. Pure alkyl halides are colorless. For example, methyl bromide or bromomethane is a colorless gas that can be used as a pesticide. However, this use is being phased out due to its toxicity. Historically, it was used as an industrial fire extinguishing agent. Methyl bromide is also known to be an ozone-depleting chemical. The alkyl bromides and alkyl iodides may develop a color when exposed to light. For example, ethyl bromide turns yellow when exposed to light and air. Many volatile alkyl halides have a sweet smell, but this may not be noticeable unless the concentration is relatively high. Lower alkyl halides, including methyl chloride, methyl bromide and ethyl chloride, as well as some chlorofluoromethanes, are gases at room temperature. Higher alkyl halides are liquids or solids. You have already studied that the carbon-halogen bond in halogen compounds is polar. Due to the greater polarity and higher molecular mass of haloalkanes as compared to the parent hydrocarbons, the dipole-dipole and van der Waals forces of attraction are stronger in these compounds. Hence, haloalkanes have considerably higher boiling points than those of hydrocarbons of comparable molecular mass. For a given alkyl group, the boiling point increases with increasing atomic weight of the halogen. This is due to an increase in the magnitude of van der Waals forces of attraction with an increase in size and mass of the halogen atom. Thus, among the alkyl halides, alkyl iodides have the highest and alkyl fluorides have the lowest boiling points. For a given halogen, the boiling point increases with an increase in the number of carbon atoms in the chain. This is again due to the increase in the magnitude of van der Waals forces of attraction with an increase in the size of the carbon chain. The boiling points of isomeric haloalkanes decrease with an increase in branching. This is due to the fact that with an increase in branching, the molecule attains spherical shape with less surface area. This results in a decrease in the magnitude of van der Waals forces and hence the decrease in boiling point. Thus, among the isomeric butyl chlorides, the straight chain isomer, N-butyl chloride, has the highest, while tertiary butyl chloride has the lowest boiling point. The haloalkanes are only very slightly soluble in water. Why? For a haloalkane to dissolve in water, energy is required to break the attraction between the haloalkane molecules and the hydrogen bonds between the water molecules. As new attractions between the haloalkane and water aren't nearly as strong as the original hydrogen bonds in water, less energy is released during this process. Thus, haloalkanes are sparingly soluble in water. Haloalkanes do tend to dissolve in organic solvents. The intermolecular attractions that form between haloalkanes and the solvent molecules have similar strengths as the attractions being broken in the separate haloalkane and solvent molecules. Alkyl fluorides and alkyl chlorides are less dense than water. In a mixture with water, alkyl fluorides and alkyl chlorides would be the upper layer. Alkyl bromides and alkyl iodides are denser than water. In mixtures with water, alkyl bromides and alkyl iodides would separate into the lower layer. Increasing the number of halogen atoms increases the density of the compounds. Aryl halides are polar molecules due to the presence of the polar carbon-halogen bond, but they are less polar than alkyl halides. Aryl halides have physical properties very similar to alkyl halides. We should make special note of the isomers of dihalobenzenes. If we compare the ortho, para, and meta-isomers of dichlorobenzene, we see that their boiling points are nearly the same. However, the para-isomers have higher melting points. The greater symmetry of the para-isomers fits better into the crystal lattice, making the para-isomers melt at relatively high temperatures. Aryl halides are practically insoluble in water and are denser than water. Here is a problem for you. Arrange these compounds in increasing order of their boiling points. Let's start by drawing the structure for each compound. All the three structures contain one chlorine atom. Since the boiling point increases with an increase in the number of carbon atoms, we would expect one chlorobutane with its 4 carbon atoms to have the highest boiling point. The other 2 compounds have 3 carbon atoms each, but one chloropropane is a straight chain, while isopropyl chloride is branched. Branched molecules have lower boiling points. So, isopropyl chloride should have the lowest boiling point. 1 chloropropane is in the middle. Haloalkanes undergo 3 types of reactions. They are nucleophilic substitution reactions, elimination reactions, and reaction with metals. Before you learn about the nucleophilic substitution reactions, get to know what a nucleophile is. The word nucleophile means nucleus seeking. Essentially, a nucleophile has an unshared pair of electrons, and it can use these electrons to make a covalent bond. Nucleophiles can be thought of as Lewis bases or electron pair donors. Nucleophiles may be anions or neutral molecules. In nucleophilic substitution reactions, a nucleophile or a Lewis base substitutes for a halogen atom in an alkyl halide. Here is the general form of the reaction. The halogen is referred to as the leaving group because it leaves the alkyl halide when the nucleophile reacts. Since the substitution reaction is initiated by a nucleophile, it is called a nucleophilic substitution reaction. Common nucleophiles include the hydroxide ion and water, both of which react with alkyl halides to make alcohols. Ammonia and substituted amines are used to convert alkyl halides into amines. Note the lone pairs on each formula. Sodium or potassium salts of alkoxides can be used to make ethers from alkyl halides. Sodium or potassium salts of carboxylates can be used to make esters from alkyl halides. Sodium iodide can be used to make alkyl iodides from alkyl halides. Lithium aluminium hydride can be used to convert alkyl halides into hydrocarbons. Some nucleophiles can be described as ambident nucleophiles. These contain two nucleophilic centers and so can link to the alkyl halide in two different ways. For example, the cyanide ion can link through the carbon atom to make alkyl cyanides. If the cyanide ion links through the nitrogen, alkyl isocyanides will form. The nitride ion is another example of an ambident nucleophile. If it links through the nitrogen, a nitroalkane will form. It can also link through the oxygen to make alkyl nitrides. Depending upon the mechanism or the reaction conditions, nucleophilic substitution reactions can be classified as SN1 or SN2 reactions. The S is for substitution and the N is for nucleophilic. Since these reactions are initiated by the nucleophile, the number gives information on the reaction kinetics, 2 for bimolecular and 1 for unimolecular. Let's start with the SN2 reaction. The reaction between 2-iodobutane and hydroxide ion to yield 2-butanol is an example of an SN2 reaction. This reaction follows second-order kinetics, meaning that the reaction rate depends on the concentration of both the nucleophile and the alkyl halide. As the slow step or rate-determining step involves two molecules, the mechanism is termed as bimolecular. This reaction occurs in a single step and does not involve any intermediate. Take note of the three-dimensional arrangement of the atoms around the carbon in the alkyl halide. The solid wedge is used to show the bonds coming out of the plane of the screen. The dashed lines show bonds going down the plane of the screen, while the straight lines represent the bonds in the plane of the screen. In the SN2 mechanism, the nucleophile attacks from the back of the molecule on the opposite side from the halogen atom, the leaving group in this reaction. The leaving group leaves simultaneously. This is described as a concerted mechanism. That is a one-step mechanism, because the new bond between the nucleophile and the carbon atom forms at the same time as that of the carbon-halogen bond breaks, as shown in the pentacoordinate transition state. Since the carbon atom is bonded to 5 atoms, the transition state is unstable and hence cannot be isolated. As the bond between the nucleophile and the carbon atom forms, the bond between the carbon and the leaving group weakens. The nucleophile essentially pushes the leaving group off the carbon atom. There is only one type of product in an SN2 reaction. If you compare the alkyl halide reactant and the substituted product, you can see that they have opposite stereochemistry. This switch is called an inversion of configuration. Can you imagine an umbrella being pushed inside out by a heavy wind? This is a useful analogy for understanding the SN2 mechanism. Let's apply our knowledge of nucleophilic substitution reactions to a couple of problems. Try to answer them on your own before checking the solutions. What happens when 2-bromo-octane is treated with aqueous potassium hydroxide? Start by writing out the reactants. The hydroxide ion is the nucleophile. See how it approaches the carbon atom from behind. Notice the inversion of configuration as the hydroxide ion pushes the bromide ion out to make 2-octanol. What happens when methyl chloride is treated with potassium cyanide? KCN is ionic, so it generates a cyanide ion which attacks the carbon in the methyl cyanide. In principle, the cyanide ion is ambident and could attack from either end. However, the CC bond is more stable than the CN bond. So, methyl cyanide is the primary product. If we wanted to make methyl isocyanide as the primary product, we should have used silver cyanide as the nucleophile. Since silver cyanide has significant covalent character, linking through the nitrogen atom predominates. As you've seen, the reaction involves the approach of the nucleophile to the carbon bearing the leaving group. Hence, the presence of bulky groups on or near the carbon atom will hinder the approaching nucleophile. Thus, among the alkyl halides, methyl halides, due to the presence of only 3 small hydrogen atoms, are the most reactive in SN2 reactions. Tertiary alkyl halides, on the other hand, due to the presence of bulky groups, are the least reactive in SN2 reactions. Thus, the order of reactivity of alkyl halides towards SN2 reactions is as shown here. Not all leaving groups react equally well. In general, among the halogens, fluorides are the poorest leaving groups, and iodides are the best leaving groups. In these pairs of halogen compounds, which would undergo an SN2 reaction faster? Let's start by drawing out the structures. For the first pair, 1-bromohexane is a primary alkyl halide, and cyclohexyl bromide is a secondary alkyl halide. We expect 1-bromohexane, then, to be more reactive and react more quickly. For the second pair, both structures are secondary haloalkanes. However, iodine has a weaker bond to carbon than chlorine. Alkyl iodides are much more reactive than alkyl chlorides. Now, it's time to turn our attention to the other mechanism called the SN1 reaction mechanism. The reaction between 3-bromo-3-methylhexane and hydroxide ion to yield 3-methyl-3-hexanol can be taken as an example of an SN1 reaction. The reaction shows first-order kinetics, as the reaction rate depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. The reaction occurs in 2 steps. In step 1, the leaving group departs, resulting in the formation of a carbocation. This step is slow and reversible. In step 2, the nucleophile attacks the carbocation, forming a covalent bond. The greater the possibility of the formation of a carbocation by an alkyl halide, the higher are the chances for the reaction to proceed via the SN1 mechanism. Further, the greater the stability of carbocation, the greater will be its ease of formation from alkyl halide and the faster will be the rate of reaction. Thus, due to the greater stability of tertiary carbocations, tertiary alkyl halides readily undergo SN1 reactions. Allylic and benzylic halides also show high reactivity towards the SN1 reaction. This is because the allylic and benzylic carbocations formed get stabilized through resonance, as shown here. SN1 reactions are usually carried out in polar protic solvents such as water, alcohols, and acetic acid. The proton from the solvent molecules solvate the halide ion as it leaves in the first step of the mechanism. In the SN1 mechanism, there are two directions from which the nucleophile can attack the carbocation. Two different products can be formed from the SN1 mechanism. Compare the product that is formed when the nucleophile approaches from the left compared to when the nucleophile approaches from the right. They have the same formula, but different arrangements in space. These two products are mirror images of each other. They are not superimposable. Even if we rotate the right-hand molecule around the bond between the black and blue atoms, it still doesn't match the left-hand molecule. We call these as enantiomers. In the SN1 mechanism, both enantiomers are equally likely to form. This is called racemization. And such 50-50 mixtures are called racemic mixtures. You learn more about terms such as enantiomers and racemic mixtures, as well as about the stereochemical aspects of nucleophilic substitution reactions in the next module.